Good morning, good afternoon, or good evening, everyone, wherever you might be. So today I'm going to be doing something a little different from calculus. I'm going to be um, explaining this concept of scientific computing, since I'm also taking a course in scientific computing, so might as well talk about it, right? Um, so yeah, basically, and I just searched this up on Google, so don't take my word for it. Um, what AI Overview said is that scientific computing, it's basically the field of computers, obviously, has something to do with computers, and their purpose is to solve different kinds of complex problems. Oh, my head is in the way. Let's do that. So their purpose is to solve complex problems in science, engineering, and whatnot using uh, mathematical models. So, it uses mathematical models and different computational techniques, which I have yet to learn, but I know a bit because I already I'm 1 week in the course. So yeah, it employs mathematical models and computational techniques. It involves developing and applying algorithms and software to simulate, analyze, understand real world phenomena. So yeah, um, so yeah, let's just jump right into the first topic. So the first topic is actually about this thing called it's the concept of vectors and matrices. And it's not the vectors that I talked about in Calc 3. It's a bit different. I'm kidding, it's way different. So let's start. So what are vectors? So first we talk about vectors. And the definition that was given to us at least was basically a vector is something where you can store a bunch of values in. So it's like some sort of container or a column or a row, and you can store some values in. So this is a vector. At least this is how they formatted it. We're assigning it to v, and then we're putting some numbers in. So we have 1, 2, 5, and then 7.29. So these are this is a vector. This whole thing's a vector. It's like some sort of container, and you're storing a bunch of values in, right? More generally, this is a vector. V1, V2, all the way to Vn. You have values in there, all the way to n. And this vector, we have this notation, this vector belongs to, or it has a set of all real numbers with dimension n. Now we're going into a bit of notation, but basically in English, this means vector. Basically, this means it's in or belongs to or set of. And this R with a one, real numbers. And we remember that real numbers are any numbers, could be -1, could be 0, could be 500, could be 235, could be 42. All of those are real numbers. Could be a decimal number. So all of those are real numbers. What is this n? This is what we call dimensions. And I don't mean like the netherworld and stuff like that. I mean the number of rows. So this is the number of rows in this case, n. So we have n rows here, right? Because we have 1, 2, all the way to a number of rows n. Here we have 4 rows. This is 1, 2, 5. What am I doing? 1, 2, 3, 4 rows, right? So this is V has element of all real numbers with dimension 4 because it has 4 rows. Okay, so that's that. A little bit of notation going on here. But anyway, and we actually try to generalize this thing. We say that V, I'm just looking at my notes, V subset J is an element of all real numbers. And here we say that J is equal to 1 going all the way to n. So what does that mean? It starts at 1. J is equal to 1, starts at 1. It goes all the way to J equals n, which in this case, that's what's happening here. Right? It starts at 1. It goes all the way to n. Okay. And so actually, we can denote vectors geometrically. So a way to denote them geometrically is we can graph an xy plane. And we have some values here. So let's say this is 1, 2, 3. 1, 2, 3. Let's put the y above-ish. We have some values here, and we can say, oh, this value here gives us a point. It gives us the point 2, 3, right? And we can actually denote this as a vector. Let's say this is vector z, which has 2, 3. But we prefer to write it this way, 2, 3. Why? Because in computing, or at least what's taught to us is, we usually think of vectors as these kinds. So these are what we call column vectors because it goes down. This is a row vector because it's a row. It's horizontal, goes horizontally. This one goes down, right? So we used to think of vectors in the context of scientific computing as column vectors. And not only that, we can think of it in 3D, which we did talk about in my Calc 3 walkthrough videos. It's actually the first topic. So this is X, this is Y, this is Z. And here we can make points here, right? So we can say, oh, this is 4, this is 2, let's say. And then maybe this is 2.5, right? So we can make some points here. So this is the point 4 to 2.5. Let's make this. So that's the point 2, 5. 2, 4, 2, and 2, 5. How do I make this? Anyway, I was trying to make it dark, but it doesn't matter. So we have the point 4 to 2.5. And we can also say that this is a vector. Let's say this is vector W, could be any. We can write this as 4 to 2.5. Or we could write it like this, 4, 2, 2.5. So again, we have a column vector and we have a row vector. Okay. What else can we do? Let's go back to 2D. So again, I make an XY plane. I reverse the planes. So X is the horizontal axis, Y is the vertical axis. And let's say we make a curve, right? Let's make a curve. Let's say there. We have some points here. These are on the curve. I know I'm bad at drawing. These are different kinds of points. And we can actually say, let's say this is the F vector. And we have a bunch of points here that we can say about. So let's say this is a vector that contains these points, 1.1, 1.1, 1.2, 1.3. Let's just say this is 1.1. So basically the idea, and that goes on, the idea is that a vector stores things. It stores values, it stores elements, it stores integers, it stores real numbers, right? So that's the vector in the scientific computing context, which is different from a calculus context, right? Okay. Now let's talk about Matrix. And I don't mean the movie Matrix, although I think that's related. I'm kidding, I haven't watched the movie yet, so I don't know. I heard it's good though. Okay, before I digress too much, we're talking about matrices. So matrix is the singular one, and then matrices is you have a bunch of matrix. So you call them matrices. So let's say we have a matrix A. So we're just assigning a matrix to a variable. And well, let's say we have, let's say one, I don't know. Again, it stars a bunch of elements. 7, 6, 5, 2, 5, 2. This is a matrix and it stores integers, right? And what can we say about this matrix? Well, we say that it has 3 rows and it has 3 columns. I spelled columns wrong. It has 3 columns, right? And so how do we describe this matrix? This matrix has the set of elements, and these are a bunch of real numbers with 3 by 3. Okay, so this 3 is describing the number of rows. This 3 is describing the number of columns. So we have 3 columns, we have 3 rows. So this is always going to be rows by columns. Okay. Now, what if we make it general? Let's make it general. And so the way to make this general is we go from, let's do A again, A11, A12, A13, all the way to A1n. Okay, and then this is A21, and then we go down. This is A-N, A-M. No, I'm wrong. Oopsies. This is not N. This is M. And this is N. N for nice. Okay. And then this is 2, 2, 2, 3. This is 2M. We can keep going. And this leads us to NM. So this is more general. This is more of a general matrix. What can we say about this matrix? Well, this matrix has N as in nice, by M as in me, dimensions. So we have n rows and m columns, right? So if we were to apply what we found here, this is n rows. This is m columns, right? Okay, now you noticed here, I put like a bunch of numbers in every A, right? So why did I do that? Well, this is actually a way of, um, we call this indexing. Indexing meaning we say that A, and then which row are we at, and then which column are we at, right? So in this case here, let's take this for example, A11. The one here, this is which row we're at. So we're at row 1. And that makes sense because we are at row 1. This is row 1. Now what is this? This is column 1, or the first column, right? So that's basically what that indexing means. So if we say, let's take this one, right? Let me delete this real quick. Let's take this one, A, 2, 3. We're at the second row, and we're at the third column. So that's that. And so to make that even more general, we did this. This is basically n rows. We're at the nth row. I'm just gonna write it out. Nth row, and we're at the mth column M. The column M. Okay. Okay. So far so good. And what are we doing with this? Well, we can actually do this. A I J equals A I J. So this is another form of notation. So again, I'm just throwing you a bunch of notations. But yeah, these two ways are the same. The idea is indexing. So based on this notation, we can determine which row we're at, and which column we're at. Okay. And another way of looking at it could be maybe this kind, and this is just 2, 3. So any of these ways, but the idea is we're indexing. Okay. And yes, we described it. It's n nice, n by m minion, n by m dimensions. So we call these dimensions. Now, if you might be wondering, how about our vector? Well, this is actually just n by 1 because we have only one column. But we don't need to write that because we already know. By default, then that's one column, right? So that's the idea. Okay. Now, let's say we want to talk about adding vectors. Let's say we want to do that, right? So I have this vector v, and here you notice I put like a horizontal line above. Did I do that? Yes, I did that. Oh, I forgot to talk about it. If there's a horizontal line above the letter, it basically means it's a vector. Another way, it's just notation. Another way you can say this is a vector. Another way could be in bold. I can't do bold. That's a vector. But in our course, we stick with this. So I'm gonna stick with this. then you'll know it's a vector. And what can we say about this vector v? Well, it has n rows, n for nice, n rows, and we have this vector w, and it has m rows. So these are still rows. We're talking about rows here. Doesn't mean if it's letter n for nice, it's rows. And doesn't mean if it's m for minion, then it's columns. It still depends on where you place them. So here you place them at the beginning. So by default, these are rows. We just changed the lettering because we're mathematicians. So we want to make the lettering different, I guess. So okay, we want to add these two vectors. That's what we want to do. And so how would that look like? Well, if we add them, let's make it general, yeah? So we have v1, v2, all the way to vn, because we have n number of rows, and we're adding it to w1, w2, all the way to wm, because we have m rows based on this one. And so yeah, that's basically the idea. You're just adding the rows, and you're gonna get some vector out of it that contains the total of each of these. v1 plus w1, v2 plus w2, all the way to vn plus wm. But what's the condition? We have a condition here, and that is letter n for nice should be equal to letter m for minion. Why is that? Because let's say one of them is greater. If one of them is greater, let's say n is greater, what can be added with? We can't add it with anything in our w vector. Or let's say one of them is less than. So that's the idea. We want to make them equal. We want to make them with equal number of rows. So n should be m. So technically, we can actually write minion as nice as n, right? But that's the idea. We want them to be equal. And similarly with subtraction. So if we want to subtract, then same idea. We're just subtracting v1 from, no, we're subtracting w1 from v1. So that's v1 minus w1, v2 minus w2. So yes, that's the idea. Okay, how about if we add the same vector v together? Well, that's the same idea. We add these two, v1, v2, same thing. We can actually simplify this. We can just say twice the thing. So 2v1, 2v2, all the way to 2vn. So we can actually simplify that thing, right? We're gonna move it here. And we can actually factor out the 2 from the vector itself. So we have v1, v2, vn. Yeah, we can do that. So yeah, that's the idea of adding vectors. You're adding them based on their corresponding position, their corresponding row. So you add row 1 vectors to get row 1 elements together, row 2 elements together, and so on and so forth. So that's that idea. So now we talked about adding / subtracting vectors. Let's talk about this thing called dot product, which there is a calculus concept for this, and it's actually quite similar. But we're also going to talk about, which I just learned here in this course, not even in calculus. It's called the outer product. So actually, fun fact, dot product is also known as inner product. And so we have an outer product. Very original. Okay, so for dot product, well, if you guys were watching my calculus course, we're getting the dot product of two vectors. We can actually write them this way. This is from calculus. You can write them this way. So these are just notations at the end of the day. Doesn't matter. But the idea is from V1, we multiply it to W1, V2, multiply it to W2, and we go on until we reach V, let's say Vn, until we reach Wn, right? So here, let's actually characterize the vectors a bit so that we know what we're dealing with. So we're going to say that this V vector as well as this W vector, they're both um, real numbers and they both have dimensions n. Okay, so we're going to keep doing this dot product and we can actually put more notation here. And I don't like notation because it makes me look impossible. It makes it look hard. But actually, this is really simple. This is summation. So I'm just going to write it out first and I'm going to explain it. But it's this E looking thing. Or is that, was that like Greek E? And let's say we do J. We start at 1. We go all the way to N. And we have VJ, WJ. Now, what does this mean? So here we start at J equals 1. We start at J equals 1, so V1, W1. And since we're doing, we call this summation. So we are actually going to continue adding or incrementing or adding this J by 1. So our first one is V1, W1. Then we're going to add. And then now J is going to be 2. So we're going to say V2, W2. So at first J is 1. We plug that in here. So V1, W1. And then the next thing is that J is going to be 2. And then we add it again. Here, J is 2. We pop the 2 in there. So we have V2, W2. And we go all the way until we reach N. And so J is now N. We plug in the N here. So Vn, Wn. So that's the idea of summation. It's just a way to make things compact, to make equations compact. And there's also this idea of transposing. What do I mean by transpose? So remember when we talked about vectors being, they can be row vectors and column vectors? Well, this is what transposing does. If we transpose a vector, initially it's a column vector. Let's say it's a column vector, V1 all the way to Vn. If we transpose that, this is going to be then a row vector. And if we transpose a row vector, then it's going to become a column vector again. So the idea of transposing is kind of changing the format of the vector. So in this case, the notation for this is actually a bit funny. So we have this vector, right, with the line. We have this capital T, which I'm assuming T is for transpose. And here we kind of assume that, so we start off with V1, V2, all the way to Vn, which is now going to be V1, V2, all the way to Vn. So that's the idea. When we transpose something, we're basically changing them the format from a column vector to a row vector and vice versa. Okay. Now, so that's inner product, and now we talk about outer product. And what outer product is basically Let's say we have vector v again, and there's this notation of outer product. It's like a circle, then you put an x in it, and let's say we're getting the outer product of vector v and vector w. And so what is that going to look like? Well, let's start with numbers because I don't want to get into this without numbers. So let's say vector v has 1, 2, and let's say vector w has 3, 4. They're both column vectors by default. Okay, and now how do we get the outer product? So actually, when we get the outer product, it's going to be a matrix. So if we get the dot product, I mean the outer product of two vectors, then we're going to basically end up with a matrix, right? Okay, now I'm trying to find an example here. Okay, so let's say we have those two, right? And um, hmm. Actually, let me check. Can we get the outer product if we both have column vectors? If we have both column vectors, can we do that? Because I only tried it for a row and a vector. Oh, actually oh no, we can't. I don't think we can, no? Yeah, yeah, we can't do that. We can't. So basically we have to transpose. So that's the idea of transposing. We're going to transpose one of them, and that's how we're going to get the outer product. And it's actually different if we so we have to if we transpose V, then we're gonna have a different answer. Okay, let's try doing, let's say I want to transpose W, right? So let's say I'm going to transpose W. And then this is going to be a row vector with 3 and 4. Now, how do we do this multiplying thing, right? So actually, if we then get the outer product of this thing, it's simply going to be so the way I think of this is I go through um let's say the first vector, the first element, and then I multiply it to each of the elements in the row vector. So that's how I like to think of it. So what's gonna happen is that I'm gonna multiply 1 by 3. That's my first thing. Then I'm gonna multiply 1 by 4. That's my second thing. And then I'm done. Now I'm gonna move on to the next row for vector v. I'm gonna move here, and then I'm gonna multiply this to here and here. And then that's what I'm gonna write. So 2 times 3, 2 times 4. And we can compute that. So that's 3, 4, 6, 8. So that's my matrix after computing, right? Now let's say, what if we did it the other way around? So, that's interesting. If we did it the other way around, let's say v, let's say we transpose that thing. So from 1, 1, 2, this becomes a row vector of 1, 2, and then w stays the same. So now we're multiplying this row vector to this column vector. Now, how do I want to look at this? So let's say V, we get the outer product of vector V and W. So how this is going to work is I'm going to look at this thing and I'm going to multiply it to this thing. And then the product I get from there, I'm actually going to bring it down. So I'll show you. So what's going to happen here is that I'm going to multiply 1 and 3. Okay. Now I'm going to move. I'm going to go to 2. And then from 3 here, I'm going to go to 4. Now I get 2 times 4. Done. That's it. So this is going to be 3, 8. You see how the difference is? Those are different. So ordering matters, right? If we transpose V, we got vector. If we transpose W, what do we got? We got matrix. Now, mathematically, how is this possible? Okay, let's look at the first example where we transpose W. So here V, right? What's V? What's the characteristic of V? V has 2 rows, right? 1, 2. How many columns? 1. So 2 by 1. While W, we transposed it. W has how many rows? 1. How many columns? 2. So if we were to get the outer product, what we're actually doing here is we're getting this piece x this piece. So it's going to be 2x2, right? So the cross, why did I say cross? The outer product of these two is actually 2 by 2, right? See, that's fascinating. 2 by 2, because this has 2 rows, this has 2 columns. Boom, boom. Right? Now let's look at this other case. Here we transpose V. Let's look at their characteristics. What's V when you transpose it? This has 1 row, 2 columns. Now if you look at W, W has 2 rows and 1 column. Right? And so if you get their what's this? Their outer product, well we get, oh yeah, we get 1 by 1. That's funny. Yeah, here this is weird because we actually get 2 by 1 instead of 1 by 1, right? So, that is interesting. I'm actually looking at my notes. I don't know why that happened. But yeah, I mean, that's what's going to happen. It resulted in a 2 by 1. So we can actually generalize this idea. So, okay, let's generalize the idea. So if we get, let's say the outer product and we transpose W, right? So let's say we get the outer product, but W is transposed. Then we're gonna get uh an R. Actually, let's characterize this. Let's put characteristics, yeah. So I'm gonna say that this V, um, yeah, I'm gonna say this V has N for nice, N rows, and this W has M rows for minion, M for minion. If we transpose this thing, the moment we transpose this thing, well, this will now give us what? From M by 1, it's going to be 1 by M. This one stays N by 1, right? So that's what happened if we transpose this thing. So as a result, if we get their cross product, what do we have? Well, we actually have N by M. Confusing. But we can actually make this okay, so I'm gonna erase this. Okay. Let's actually see this in action. So we have a vector v1 all the way to vn, and then this w transposed. So we're gonna transpose. If we transpose, this w1 all the way to wn is going to be w1 all the way to wn in the row. And what did I say about multiplying these things? So if we get their outer product, well, there's actually just, so we go through this and we go through here, right? I think that's what we did, right? Yeah, that's what we did. I think. 1 times 3, 2 times 4. Oh no, it's the other way around. Yeah. So I'm gonna log my previous example. I shouldn't have deleted it. I totally forgot what I was gonna say. Um, okay, let's wait for it. Oh, too late. Guess I can't go back. Okay, I'm just gonna look at my notes. So I'm looking at my example again. Okay. Yeah. So if we transpose, then so let's say we transpose this. We have W1 all the way to WM, which will now be a row. And what's gonna happen here is I'm gonna look at this thing, and then I'm looking at that thing. So actually the cross product of this thing, but here it's T that's transposed, it's going to be a matrix. N by M matrix. This is going to be V1, W1. Right? And I'm gonna continue. I'm gonna look at 2, but I'm still in V1. So V1, W2. Right? Then I'm gonna continue until I reach V1, WM. And then here I'm going to continue until I reach Vn, W1. Then if I slide all the way here, this is Vn, WM. Right? Right. Okay. Because this is the one I transposed. Now, what if it was the other way? So if it was the other way around, where I transposed, let's say I transposed V. Oh, I managed to bring it back. Yay. 1 times 3 times 4. Nice. Wait, did I get that right? Oh no, this one's different because I transpose D. Okay, okay. Maybe I shouldn't have erased that. Scrap it. I'm not gonna put it down here just in case. This is what I'm gonna do next. Okay, so again, let's try it this time when we're um transposing V. So if we transpose V, so let's say I'm gonna transpose this thing. Let's say initially it was n by 1. Now if we transpose that, then it's gonna be 1 by n, right? And let's say our W stays the same. So our W has m rows by 1 and m by 1. I'll just call it m. Okay, I probably need to put this here for extra space. Okay, now what do we want to do? We want to get their outer product. So V and W. What is that? Well, we actually can't figure out the characteristics just yet. So we want to try to look exactly at how this works. Okay. So let's say, I'll do this after. Let's say I'm going to visualize what this actually looks like. If we transpose V1 all the way to Vn, that's going to be a row vector. And if we let W as is, it's going to be a column vector. M. Right? Now I probably should have. I'm going to put this a bit more down. I'm going to put a bit more down here. Okay, that's for reference. Okay, now we want to get uh, their cross product. So what's that going to look like? Well, it's going to be a vector like this, V1 all the way to Vn, W1 all the way to Wm. And here, we're just going to multiply this thing by this thing. So that's what's happening. Let me see if I got that right. Yeah, instead if I transpose V, then yeah, I should get that, right? Not super confident, but yeah, I probably should get it, kind of. Okay, so whoopsie daisy. Yeah, okay, I got the first one right when we transpose W. Okay, so um, yeah. Wait. If we transpose V, what's gonna happen? It's treated as a row vector, and it flips the rows and columns. Okay, I'm gonna ask. You're right. Concrete for outer product. Yeah, I do better with numerical examples. If V is transpose and W, and also N, and also the other way. Let me just, okay, let's do, yeah. So actually, funny enough, we if we transpose the first vector, we're actually not getting an outer product. Matter of fact, um, we're actually getting. I'm gonna write that up. We're getting a dot product. Now that I just realized, yeah, we're getting a dot product. Funny, right? Why is that? If we do this, we're multiplying this, and then we're adding it. So what's happening here is that we do V1, W1 plus V2, W2, all the way to Vn, Wn. We assume that n is equal to m. Because if that's not equal, then that's not possible, right? So this is just, we can write it in summation actually. So this is just, we'll write summation all the way to, let's say n, doesn't matter. J starts at 1, so we have Vj, Wj. So that's our summation, right? So that's what happens when we transpose V instead of W. We will get a dot product. This is not an outer product. It's a dot product. But in the first case, it's an outer product. Yeah, because we're multiplying it like this. This times this. Okay, I think that's all about outer products, I believe. Yeah. I'm also doing this because I'm honestly a bit confused with some of the parts of this course. But yeah, I think that should be it for outer products. Okay. Yeah. Yeah. Okay, cool. Um, Now I'm going to move on to some more jargon here, which is funny. But I'm just gonna explain this bunch of extra. So I think these are just like extra stuff. Oh, don't know why I made it. But these are just like what? Extra stuff. Extra stuff to know about vectors and matrices in general. So let's say we have A and it has n by m dimensions. So now we know from here this is a matrix. Could be a matrix. Unless m is 1. I don't know why I wrote it like an n. M, if m is 1, then that's probably a vector. No, it is a vector. And then let's say we have b, and this is what? P by q. So here we're just using different names, but they mean the same thing. Okay, and let's say, oh, now I know what we're dealing with. We're actually dealing with matrices this time, because last time we were dealing with vectors. So let's say we have some C, uh, ij. So again, indexing. C here is basically A plus B. And this is equal to what? A ij plus B ij. And this makes sense, right? I mean, we're just adding matrices here. Now I need to look at conditions. What are the conditions for this to work? When we're adding, let's say we have A. Let's say we have, I'm gonna put numbers. 1, 2, 3, 4, 5, 6. Right? So you have B. Let's do the same thing. 4, I'm kidding. I'm making it simple. 1, 2, 3, 4, 5, 6. Easy, right? Let's make the numbers simple. How do we add this thing? Matrix C. We're adding it per element, right? Okay. I'm actually, yeah, I just realized I don't know how to add matrices, which is funny. But it should be simple. Okay, so we're actually just adding them. Ooh, might be wrong here, but oh no, I'm right. I'm right. You simply add each element in the same position. So that's what we're doing. So we're adding 1 plus 1, 2 plus 2, 3 plus 3, and so on and so forth. So we get 1 plus 1, 2, 2 plus 2, 4, 3 plus 3, 6, 4 plus 4, 8, 5 plus 5, 10, 6 plus 6. I don't know, 6, I'm kidding. 12. That's our new matrix, matrix C. So actually, we have a condition here because what if, let's say this is n rows, right? And let's say we have more columns. So if we have more columns, am I saying it right? Oh no, no, no. So actually, here we have n rows. So let's say this is n, or let's say this is 2. And let's say this is p, this is 2. This works, right? So basically the idea is n should be equal to p and m should be equal to q. Both matrices have to have the same columns and the same rows. Same number of columns and same number of rows so that we can add each element to its corresponding. I keep saying element. Yeah, each value from matrix A to the corresponding value in matrix B. So that's the idea. N should be equal to P. These two are equal. These two are equal. Okay, what else? What other extra stuff do we have? Oh, look at that. We have S. Yeah, that's a cursive way of writing it. Like said. Said. Oh, been a while since I've written cursive. Said. Yeah, I think this is just a it's been a while since I've actually written cursive. Okay, so we have that, and this is a scalar. We call it a scalar because we just multiply a scalar to a vector. Now, how does that look like in action? Let's say we have a vector. Let's say I have wait, why am I saying vector? Let's say I have matrix 1, 1, 1, 1, 1, 1, right? And so if we add a scalar to that, let's say my scalar is 2, and we just multiply 2 to each of this. So that would become 2, 2, 2, 2, 2, 2. We're multiplying 2 to each element in the matrix A. So yeah, extra stuff to know, good to know. Moving on. Now we're going to talk about something in linear algebra that I have yet to fully learn, and we call this the concept of multiplying matrices. So if we want to multiply matrix A and B, how do we do that? Right? I mean, I haven't learned that in my calculus course, but we're gonna learn it here. So let's try doing something basic. Let's do numbers. So let's say my A, keep going with A. This is 1, 2, 3, 4. Let's say I have my B. 4, I don't want to do 6. 4, 2, 3, 1. Now, if we multiply this, how would that look like? Well, the idea is to basically multiply this by this. So let's say their product is C. Let's just say it's C. If we multiply 1 and 4, what do we get? 4. Right? Moving on. We multiply 2 and 3. Right? If we multiply 2 and 3, I'm actually going to look at an example. Example of matrix multiplication. I'm still learning. Okay, give us a. Oh, oh, okay. So funny enough, it's a dot product. Yeah, it's a dot product. Let me go 3 by. Whoa. Okay, so it's a dot product. Yeah, it's a dot product. Okay, I'm gonna do it. Let's try the example that I asked for. I'm actually gonna change the numbers a bit. Let's see what happens. See if I get. If I don't, let's try again. So 5, 6, 7, 8. That's the example that was given. So it's kind of like getting a dot product. So what that means is I'm gonna multiply 1 and 5. So that's 1 times 5. That's the first one. And then I'm gonna move to let's say 2 and 7. Why did I say 2 and 7? Oh, okay. So it's actually row and then column. And then how does that work? I'm gonna add that. Amazing, right? Very interesting. Okay, step by step. Boom, we're done. Next, we go 3. Where do we multiply 3? By 5. Again. So it's uh 3 times 5. Then we're adding it to 4 times 7. Maybe, huh. Actually, we could have just done purple here all the way. Do purple all the way. And then we have 4 here. Okay, so this is 4 times 7. Right. Next, we go back. Now we're doing the first row again. 1 times 6. So 1 times 6. We're adding that to 2 times 8. So you see the idea? We're like going through here. We're multiplying it to the corresponding column. I'm kidding, not column. The column here should be the exact position of the row. So this were row 1, row 2, column 1, column 2. We're multiplying column 1 by row 1. And then column 2 by row 2. And then we're getting the total, and then we're storing it this way. Finish that first column, we go to the next column. So if we start at column 1, yeah, if we start at column 1 of this thing, we start at column 1, we finish column 1. Then we move on to column 2, we do that thing, multiply column 2, then here, finish it here. Okay, let's continue. So where were we? Let's say we have, where was I? Oh, okay. So here we're actually at 1 times 6, 2 times 8. Okay, next, 3 times 6, 4 times 8. Right? So 3 times 6 plus 4 times 8. And we're done. Now let's make a general statement. Let's say let's say A has okay, I'm gonna do something different from the notes that was given. I'm gonna characterize this. So I'm gonna say um oops, like I'm gonna say A is a matrix n by m dimensions. And I'm gonna say B is also oh, I did that. B is also a matrix that's P by Q dimensions. So what are the conditions? Well, after we're multiplying all of that stuff, we realize that the number of columns of A should be equal to the number of rows of B. So the number of columns of A should be equal to the number of rows of B. So we're saying M should be equal to P. Now, what else do we realize? Well, if we're going down, so we're saying N, we're actually, well, we're doing the same thing actually. But yeah, I mean, when we're multiplying boom, boom, plus boom, boom, right? Should be the same. And then we move boom, boom, and then boom, boom. So again, the number of rows of A should be the same as, oh, number of columns of A should be the same as the number of rows of B. Okay, that's pretty interesting. And then what if we move to the next column here? So look at that. Boom, boom, and then boom, boom. 1 times 6 plus 2 times 8. Okay, I actually can't tell the difference, but is M supposed to be equal to Q? The number of columns of A, does it have to be equal to the number of, no, I'm kidding. The number of rows. So what I'm saying is that, or what I'm asking, the number of rows of N here, should it be equal to the columns of this guy? So this is what, Q, I believe. Yeah. So I'm gonna say, I'm gonna ask, can you generalize that? Yeah, I want to see a general. Oh, so it's only columns of A, which should be equal to columns of B. I'm gonna ask, does rows of A have to be equal to columns of B? I don't think so. I don't see a relationship of some sort. Probably if it were the other way around, then yes. I don't think so. Yeah, it's only the number of columns of A should be equal to the number of rows of B. Yeah, that's it. Yeah, that's it. So the idea behind matrix multiplication. We're gonna put like secretly dot products. So that's basically just dot products, right? Okay. Now I'm going to move on to what my notes is saying, what we discussed. So I'm just gonna go straight into that and mind blow myself with the number of letters and notation I'm seeing. Okay, I'm gonna walk through it really slowly. So AB, we will just multiply A and B. Um, what do we know about AB? Okay, to make it general, this is A11. Remember, this is our indexing. Row one, column one. We go A11, A12, all the way to A1N because we've reached the M column, right? M. Okay, we go down. A21. And if we continue down here, we're going to reach AN1. We're still in the first column, but we're in the nth row. And then we can continue, and we're going to reach here NM. We're going to reach NM. NM. So that's our our A matrix, and we're multiplying it to B. So B11, B12, all the way to B1Q. Because we've reached the Q column, then I'm gonna go down. So B21, all the way to B I'm dyslexic. I'm kidding. BP1. And this is BPQ. I'm gonna add dotted lines just to show this is the idea. And so we're multiplying that, right? Now, what do we notice? Let's first try doing N. So first we're going to try doing A, B, N. What do I mean by N? We're gonna try doing it for okay. We're gonna try doing it all the way to we're basically doing it for one row. So we're doing it here and we're doing it here. We're getting the dot product of that. Okay. That's what this means. So let's do that. So we have A11, we're multiplying it to B11. We're gonna add A12, multiplying it to B21, right? B21. And then we're going to continue until we reach A1M, BP1. And what's our condition here? Our condition is that M should be equal to P, right? The length of this thing, or the number of elements in here, should be equal to the number of elements in here. So A's columns, matrix A, columns of matrix A should be equal to rows of matrix B. That's what that basically means. All right, now I don't know why it says N. That's funny. But anyway, I would have said like what? Like M or N? I don't know. M or P. I don't know why it says N there, but anyways. Okay, we're gonna continue. Oh, the blue. Interesting. We can simplify this with a summation. So again, we're gonna put this weird E there. And then we're gonna say, let's do L. Let's letter L. L is 1, and we're going to do it all the way until we reach M. So A reaches M in terms of columns, and B reaches P in terms of rows. So how does that look like? A1L, BL1. And again, same condition. M should be equal to P. Right? This is our it's kind of like our moving part. So this becomes, it starts at 1, goes to 2, goes to 3, all the way to M, which is the same as P. Blah blah blah. So we reach M and P at the end of that summation technique. So that's a way of simplifying it. So that's doing it for, I guess, one iteration. We're doing it for one iteration. We're doing it for here and here, one time. But then we know when we're doing a matrix multiplication, we're also going to do it here and then here. And then we're going to do it all the way to here and then here. And then we're going to go back again. We're going to do here to here. Here to here, all the way until we reach here to here. And we're going to do it all the way until we reach this thing. So that's what, what did I do? So that's what matrix multiplication is. And here we're just making it general as we can. Now let's actually translate that whole thing that I was just saying. So instead of just n here, we're going to do it. So here's the notation. ij. What I just described. That process of doing it not just n times, but more than that. We're going to do it until we reach this thing. And until we finish all of these and getting the dot products to here. Right? Okay, so that's what this means. And actually, it's kind of simple. Once you already have the summation, we can just use that. So we're going to use summation because we can't write all of that, obviously. We're going to reach M, right? L starts at 1. And here we have A, I, L, B, L, J. That's it. So it depends on what row we're at, row I we're at for A. And it also depends on what, am I saying it wrong? No, I'm saying it right. It also depends on what J column we're at for B. Does that make sense? Hopefully, because I think it kind of made sense to me. But this was, yeah. I mean, I was just throwing a bunch of notation when I took this class, so I'm like, I can't. I need to really dig deep and look at this properly. Okay, and actually, what if we reverse the thing? So if we reverse this thing, we still have ij. We're basically reversing the idea. So now we're looking at this, and then we're getting the dot product of that to here. And then we're looking at this, get the dot product to here. And then all the way until here, get the dot product to here. Then we go again. You go here, now you go second column. So here, notice that for A, this time we're looking at the columns. For B, this is the one that we're doing the row thing, right? So actually, in summation, this is easy. Okay, so let's do our summation. L starts at 1. Now here, if we look at it, we're just going to switch B and A. B is now IL. A is now LJ. We just switched the matrices. Now what A is doing, B is doing. What A is doing, B is doing. What B is doing, A is doing. Okay, I just made a tongue twister. Now, what's this part? Well, this was M, right? Why was it M? Remember when we characterized this? We're doing it until we reach this M here. So we're doing that piece of getting the dot product until we reach M. Now here we're doing it until we get Q. So that's how many times we're doing it, right? So this is Q. So yeah, a bunch of notations which are thrown. But yeah, that's the idea. Okay, now let's move on to something a bit more unique. Okay, we're still gonna multiply matrices, but this time we're multiplying. So I'm gonna say multiplying matrix by a vector. So that's what we're doing this time. Okay, so how does this work? Well, let's say we have a matrix A, right? First, let's characterize. What are the characteristics of A? What are the dimensions? So let's say we'll do A is a matrix with n by m dimensions. X is a vector. Okay, which has m rows, minion, m rows. Now let's say I want to multiply those two. Let's multiply. I'm going to go with a general statement. Hopefully. Let's see if it makes sense. If it doesn't, I'm going to go with a numerical. Let's try going for general. Okay, so if we multiply, let's do A. So let's say A starts at 1, 1, 1, 2, all the way to 1m. Because these are the number of columns, right? And then here we go down. A 2, 1, A n 1. Because we have number of rows. Then here we continue. A 2, 2, all the way to A 2, m. We can skip these parts. This goes to A n m. And to, yeah. So this is our A matrix, and we're doing a multiplication of that matrix with the x vector. So x starts at x1, x2, all the way to xm. Because this has minion m, m rows. This is equal to, let's try this first one. So the first one, what are we doing? We're getting the dot product of this one to this one, right? So let's do that. How does that look like? That's going to be a11 times x1. We're adding a12, x2, all the way to a1m, xm. In summation, we're doing it all the way to m, right? And our L starts at 1. L starts at 1. So we start here. These pieces are the ones that are moving. So we have A1L, XL. So that's the summation that we're doing, right? Okay, so to make it easy to look at in the eye, we're just gonna say summation. We're not gonna fill in the stuff anymore. We're gonna say A instead of L, let's do J because that's what's in my notes. Honestly, it's fine. We can say we can change this to J. We can change this to J. That's totally fine. So I'm just gonna do that. 1J X J, right? So that's that. And then here we just changed that to 2. That's the only difference. From 1, we just change it to 2. So this next one is also a summation, but we're doing 2 instead. A2J instead of A1J. And we're doing it all the way to a summation of ANJXJ. Right? What do we get? Actually, this AX that we got, if we characterize this thing, it has what? N rows, right? 1 to N. You can see that here. 1, 1 to N. Okay, I'm corny. 1 to N. 1 to N. Um, and so this is N by 1. So actually, fun fact, if we multiply a matrix by a vector, we get a vector. Because at the end of the day, this is a number, this is a number, this is a number. So that's the characteristic of the product of a matrix and a vector. So that's that thing. Okay. Um. Okay, more facts here. Don't know why I put these, but we're gonna look at them anyway. So I'm just gonna say, I think we already discussed this, didn't we? Yeah, we already discussed this. Okay, now let's do counting operations. Operation count. So what's the deal with this operation count? Well, we're counting the number of operations that could happen because if we write our programs, that's how we'll determine how fast a program is. So if we have more operation counts, then our program will be slower. If we have less operation counts, then our program will be faster. Right? Because if you do, I mean, simple example really. If you do a lot of stuff compared, if let's say you do a lot of chores, house chores, and here your friend is just sleeping, and he probably does like what, one chore, and you guys do it in the same day. Who will finish first? The one who does more chores or the one who does one chore? Obviously, the one who did one chore. They're gonna finish first compared to the person who's doing a lot of chores. So that's the idea. If we have more operation counts, our computer program is slower. Less operation counts, our program is faster. So that's how do we concretize this concept of operation count? Well, some operation counts could be like what? Like adding, subtracting, multiplying, dividing, right? These are operation counts because we're doing something. Okay, so here we're going to apply the concept of counting operations in the context of vectors and matrices. So let's do that. So let's say we have a matrix A, always going to be A for some reason. I don't know why it's A though. Okay, so we're doing n by m. So n rows, nice, n for nice rows, and m for minion columns. Okay, we have x which has m by 1. So we have m minion rows, 1 column. So it's a vector. This is a vector, right? Let's say we want to count the operations. So there's a notation again. It's OP. We want to count the operations when we multiply this matrix with this vector. We multiply matrix A with vector X. How do we do that? Well, okay, so an important note is whenever we do an operation count, we're basically getting what's the most dominant thing in that operation. Now, what do I mean by that? Well, let's give an example. Let's say their operation count is denoted by this function, m squared plus m plus 5. What's the most dominant term out of these three? The most dominant is the one that's going to increase over time as m approaches infinity. So here we actually play the role of calculus. So if m becomes bigger and bigger and bigger and bigger, let's say we reach like 10K, right? Or we reach like a million or a billion. What's going to be the term that matters the most? Well, obviously, it's going to be this, m squared. We're going to come to a point where we don't even care about the 5. 1,000 is not as different as 1,005. We don't care about the 5 anymore. And same goes with this m. So the most dominant is going to be m squared. And we can actually denote this. So this is kind of computer science, but we have this thing called big O notation. This is where we denote how fast a program is. And so this is O of m squared. And so there's this thing in computer science where this is what we call a time complexity. Now, I'm not going to write that out. It basically means if you have, let's say, O of m squared, oh, your program is running in quadratic time. If, let's say, your program is in O of n, O of m, could be any though. The letters could be m, n, o, p, q, r, s. Let's say if it's O of m, then it's running at constant time. Because whatever we plug in for m, it outputs the same thing, right? And let's say we do O of 1. 1 is constant. And so actually the fastest running time is constant time, O of 1. This is the fastest. There's actually a graph that tells us what. Yeah, there is a graph that tells us like about big O notation. And basically constant time is the fastest. Yeah, something about big O notation. I'm going to put that here. It's also for my purposes because I keep forgetting. But this idea, right? So here is all that. Input size. As input size increases, or the number of operations you give it, this means if time increases, that means it's longer time. And here, if you notice, even if the input size increases for O of 1, the time stays the same. But if you go O n squared like that, the time increases. So actually, the best running time is this constant time, right? Which is, well, it's not this. This is this. O m squared is the same as O n squared. It doesn't matter what letter you put. It's the same thing. So what's the purpose? Like, why are we studying this? Well, if we want to make programs more efficient, we can actually use this big O notation to determine how fast our program is running. And as much as possible, we definitely want a faster program. So ideally, in an ideal world, every program runs at constant time O of 1, but we know That's not always the case. So that's the idea of big O notation. Okay, so let's try some stuff here. Let's say I have a function and it takes in m. My bad. I have a function that takes in m, and this is equal to a big O notation of some other function that takes in m as well. So here we're actually determining the speed of this thing. Let's say it's equal to this thing, f of m, right? And let's say we calculate the limit. So this is calculus 1. As m reaches infinity, and we say that the absolute value of f over g, let's set some boundaries. Let's set it, it's bounded by capital M. Could be any, but yeah, we're just bounding it. And so what's going to happen here? Well, what's going to happen is that, let's say, if it reaches infinity, and we do m squared plus m plus 5 over m squared, we just calculate this limit like a calculus class, we're going to get 1, right? So even here, as m increases, our time is still 1. I'm actually, you know what? I'm actually gonna ask about this because I definitely do not get this wholeheartedly. So I'm gonna ask it and I'm gonna explain it as I learn it. Okay. Okay. So I asked GPT. This is an explanation of big O notation using limits. So we have f of m is equal to big O of g of m if the limit of f over g as m approaches infinity for some constant m, f of m grows no fast. So actually f of m is slower than g of m up to a constant multiple. And the limit reaches 1. So what does that mean? Well, f of m runs in O of m squared. So explain in simplest terms. What's the purpose? Why is this happening? Stuff like that. Um, yeah, how fast something grows. That's what big O notation is. Number of operations your code does. Yeah, it is a computer science class. How long it takes to run, how much memory it uses as the input size gets really big. Now, what's the purpose of using limits in calculus? Well, it's to compare two functions, f of m and g of m. And we want to ask, is f of m growing no faster than g of m? And if we divide, the result is a finite number. If the result is a finite number, then f of m is big O of g of m. And if the result is infinity, then f of m grows faster than g of m. So what this is saying is that f of m, if the limit is 1, f of m is constant as g of m, right? It's running at the same speed or almost at the same speed as g of m. So we're saying the speed of f of m is O of m squared. And g of m is m squared, right? So the limit is 1. So what does that mean? So this is key. What this means is that, I'm going to write it in red because that's how important this is. F of m is running at similar speed as g of m. I'm not saying they're the same. They are similar. And I mean, I already mentioned it. As this number grows and grows, as m grows, right? As it goes to infinity, it doesn't matter. Like they're both going to f of m is going to be at the same speed as g of m. F of m is going at O of m squared. G of m is also going at O of m squared. They're running at similar speed because their limit here is 1. That's what that means. Now let's say what if m approaches 0? So let's try that. If it approaches 0, okay, we have some okay, let's see. So what is this? This is the limit as m approaches 0. And okay, we're doing the same idea. So m squared plus m plus 5 over m squared. And if you compute this like a normal calculus, in a normal calculus class, this is going to be infinity. It's going to be infinity. Now, what does that mean? What does that entail? Well, if it's infinity, then actually f of m is faster than g of m. But yeah, obviously, as m gets smaller and smaller and smaller, we can definitely see the difference between these two. Like this is obviously greater than this one if we make m super, super, super small. So we know that f of m is running faster, but as our input, as our m gets big, as we put in more data, then it really doesn't matter. They're both running at similar speed. So that's what's fascinating about, I guess, algorithms. Here we just looked at them in the context of functions. So yeah, as our m gets bigger, as we put in more data, as we put in more code, then we really have to check how fast is our program running. So yeah, that's it for today. I'm gonna be going over more stuff on scientific computing maybe tomorrow. Yeah, probably tomorrow. Or I might continue my calculus. So, but yeah, I'm really looking forward to learning more about both calculus and scientific computing. So stay tuned for those videos. Okay, I'm gonna stop sharing now, and I'm gonna see you guys in the next one. Let's stop. Okay, see you guys.